Hello. We're going to look now at artifacts associated with the ultrasound beam. These artifacts occur because the beam isn't perfect. What I would mean by a perfect beam would be a beam that is infinitely narrow, so that we know precisely where the ultrasound is travelling in the tissues, and echoes can be displayed in exactly the right spot. We'll look first at the effects of beam width. As you know, the beam has a finite width. The beam can be focused better if we have high frequencies, but sometimes we're forced to use relatively low frequencies and the beam width can be quite significant. Consider a beam sitting in one particular position. Anything within that beam that produces echoes will be displayed in the image. So any object at all that falls within the beam will be displayed. The machine calculates the depth from the echo arrival time, so it can be displayed fairly accurately in depth. But, as I have already explained, because the machine can't determine whether things are in the center of the beam or to one side or other of the beam, every object is displayed as if it came from the center of the beam. When the beam moves from one position to the next, the size of that step is quite small, so beams overlap very substantially. This means that each object is going to be seen multiple times and therefore displayed in the image multiple times. The depth will be correct each time, but the lateral position will be slightly different each time because the beam has moved. Let's have a look at a simulation showing how this works. This shows the beam on the left, and on the right-hand side the line of sight representing the center line of the beam, displaying the echoes from these two objects. So you'll notice that as long as each of the objects is within the beam, it will be displayed. Each of them therefore is displayed multiple times, resulting in straight lines within the image. This is clearly a linear probe. If it were a curved probe or a phased array probe, then each of these points would be displayed as a curved line instead. Notice that the more superficial of the two objects produces a shorter line because it is sitting at the focal point of the beam, so the point where the beam is narrowest. The deeper object produces a longer line because it is at greater depth where the beam is wider. In fact, it's easy to see that the width of the line displayed on the image is equal to the width of the beam at that depth. So we can say that every point is smeared out laterally by an amount equal to the beam width. Here's an image from an ultrasound phantom. This phantom contains soft tissue mimicking material, but we're particularly interested in the point targets, which are nylon lines perpendicular to the scan plane. These are very small nylon lines and they should ideally appear in the image as dots. As you can see, this being a curved probe, they're being displayed as curved lines. Notice that the width of the lines varies, and in particular, at the greater depths, close to the bottom of the image, the length of the lines is significantly larger than further up the image. The focal point for this particular image was located at the level of the horizontal targets, so the targets that are distributed across the width, and therefore the beam is narrowest at that particular depth. So what we can see is that each point is smeared out laterally by an amount equal to the beam width. It's also extended in depth by an amount that is determined by the transmit pulse duration. What's the result of this in a real image? These are obviously idealized point targets we're looking at here. The answer is that when we're looking at a tissue interface, it's going to look fuzzy, except when we're scanning it at perpendicular incidence. Let's look at that in a little more detail. In the top here, I've got a diagram indicating a sloping interface, an interface at some arbitrary angle relative to the beam. If you imagine each point being smeared out laterally by an amount equal to the beam width, you can see that it's going to appear thicker and it will be fuzzy in the image. In the bottom, we have the special case where the beam is perpendicular to the tissue interface, so perpendicular incidence. And in that case, the smearing of the tissue lies on top of the image of the tissue, and therefore it's not apparent in the image. So while the smearing is still present, we don't see it, and it doesn't degrade image quality. So this is the one case where the lateral smearing of each point in the image does not degrade the quality of the image. Let's have a look at a clinical example. Here we have an image showing the portal vein in the liver. On the top left, the arrow indicates a relatively clean image of the vein wall because the beam is striking that at 90 degrees. The lower arrow highlights the fuzziness and the thickening, apparent thickening, of the wall due to the fact that it is very far from perpendicular to the beam. This is important for several reasons, but one of them is that it tends to degrade the accuracy of measurements. Next, we'll look at the effect of side lobes. You may remember these are unwanted additional beams that are outside the main beam. The first side lobe either side of the main beam is the main concern since it's the strongest. And I mentioned before that it's approximately 20 decibels weaker than the main beam, which is a factor of 100 in terms of intensity. So it is significantly weaker, but it can produce artifacts, and that's what I'm showing in this diagram. At the right you can see a simplified diagram of the main beam, and then the first side lobes either side of that main beam, sweeping through the tissues to build up an image. Let's suppose we have an object, which I've shown as a red dot, that produces a relatively strong echo, so that even when the side lobe looks at that object, it will produce an echo that the machine can display. The machine will display the object at the correct depth, but it doesn't know that the echo has come from the side lobe, and it therefore displays the object as if it came from the centre of the main beam. So it is being displayed some distance to the left of its true location. In the middle of this diagram, you can see we've reached the point now where the main beam is looking at that object, it sees it and displays it in the correct location. And then on the right-hand side, the beam has scanned further so that now the other side lobe is seeing that same object. So that object has been imaged by the first side lobe and then the main beam and now the other side lobe. Once again, the machine displays it at the correct depth, but now it's going to be displayed to the right of its true position. So the result of this is that the object will be displayed 3 times. Once in its correct location, and then there will be faint copies of it to the left and right of that location, equally spaced. Here's an example, an image taken through a filled liquid bladder, and you can see that we have a bright echo coming from a strong reflection in the centre, indicated by the central arrow, and then to the left and right of that we have wispy echoes at the exact same depth. So these are side lobe artifacts. The hallmark of side lobe artifacts is that you have relatively weak echoes to the left and right of a strong reflector, and these echoes are at the exact same depth as that reflector. And now we're looking at slice thickness. Just to remind you, this is the dimension of the beam across the width of the probe. So it's a dimension of the beam we don't always think about. When we're talking about the focusing of the beam, we're thinking of the focus as viewed in the scan plane. But this is a dimension of the beam at 90 degrees to that in what we refer to as the elevation plane or the slice thickness plane. Now, imagine the beam being swept from one end to the other of this linear transducer. It will be picking up echoes as it travels, and those echoes will be displayed as a series of lines in the image. The important thing to visualize is that this is going to sweep out a volume of tissue, and the echoes in the image come from that entire volume of tissue. Let's look at the right-hand side of this slide now. First, in the center of the slide, you can see an idealized picture that we may well have in our minds of what we're doing when we're scanning with ultrasound. We like to think that we're viewing a slice through the anatomy, as if we just had a paper-thin cut through the anatomy, and that was what we were displaying. This, of course, is an extreme idealization, and it's not the reality. The reality, rather, is what I'm showing on the right-hand side, which is that we have a complete volume of tissue, which, as I said before, is swept out by the beam as it travels the length of the transducer. And the echoes displayed come from everywhere within that volume, but they are collapsed onto one another to make a single two-dimensional image. This can produce quite significant artifacts, which we refer to as slice thickness artifacts. Here's an example. If you're scanning a blood vessel in long section, in other words, you're doing a longitudinal scan of a blood vessel, then it may well be that the blood vessel is smaller than the slice thickness dimension of the beam, as I'm showing here. In that case, the vessel lies completely within the volume of tissue from which we are collecting echoes. Because of this, it's possible for the machine to pick up echoes at the same depth as the blood vessel, but actually coming from the tissues adjacent to the vessel at the same depth. So the tissues beside the blood vessel will be contributing echoes to the image, and those echoes will look in the image as if they have come from inside the blood vessel. So we will see soft tissue echoes appearing to be inside the blood vessel. And of course, this mimics the appearance of thrombus. So it's a very significant concern. Let me show you an example. On the left, we have an example where there's a blood vessel that appears to be completely filled with soft tissue. This is due, as I said, to the slice thickness aspect of the beam, picking up echoes from beside that blood vessel and making them appear as if they've come from within it. On the right-hand side, the probe has been rotated 90 degrees. So now we are doing a transverse scan of that same blood vessel. In this case, the slice thickness artifact doesn't occur, and we therefore get a clean view of the vessel, and we can see quite clearly there is no thrombus, there are no echoes coming from within the vessel. That was entirely an example of slice thickness artifact. So this highlights that it can be very important to limit the slice thickness dimension of the beam as much as possible. This is where matrix probes, which I mentioned earlier, can be very valuable because they can produce a better focus in that slice thickness dimension than conventional probes. The last artifact associated with the beam is a little different, and I've discussed it before. This is speckle. It's the texture of the soft tissue in the image caused by the random combination of many scattered echoes coming from that soft tissue. It's distracting to the eye, and that makes it harder to see subtle variations in the average echo strength within soft tissues. So if you're looking for areas of abnormal tissue, the presence of the speckle can make it harder for you to see them. The machine has, therefore, several technologies built into it that allow it to reduce speckle. One of these is frame averaging, otherwise known as persistence. The idea is that each time the machine acquires a new image, it averages that with the previous image. Because there's likely to have been some change from one image to the next, the speckle patterns will be different, and when we average them together, they become smoothed out and reduced in their strength. So the speckle is reduced by using frame averaging. Frame averaging can only be used when we have relatively static tissues. If we had very dynamic tissues, it would lead to blurring because we're averaging successive images together. Another technology which very substantially reduces speckle is compound imaging. I'll speak more in detail about that later on. The idea is that multiple images are required looking at the tissue from different directions, and when these are averaged together to give a single compound image, the speckle is very much reduced. Again, this can only be used when we're not looking at rapidly moving tissues. And then, finally, some machines apply image processing to the ultrasound image once it has been produced and stored. So they treat the image as if it was a photograph that needs to be enhanced. Image processing typically will recognize edges, tissue boundaries, and sharpen those and make them clearer. And it will also recognize areas of uniform speckle and smooth out that speckle. So these are the three technologies that can be used by the machine to reduce speckle, to make it more acceptable and less distracting. So in summary, we have looked at the effects of beam width and the way it causes every point to be blurred horizontally. We've looked at side lobe artifact, slice thickness artifact, and the question of speckle and how it can be reduced.